So let's talk about this. When we enter a room, we see a burning candle. The candle's burning at 1 inch per hour. How long has the candle been burning?
We don't really know that.
What do you need to know?
How
We need to know the starting point of the height of the candle. And so when we talk about carbon-14, we need to know the starting amount of the C14 in the fossil. Same principle, okay? So if we find, say, 1,000 C14 atoms in a fossil, do we know how much C14 has decayed?
No.
No clue. No, we must know the starting point of C14. So there are some traps in this, right? It's not clean and straightforward. So when you start the C4 dating clock, what happens is that C14 and C12 are used in the carbon-14 data. C12 is common carbon, C14 is radioactive carbon, operates the same in all our chemical reactions, and the C14 is stable, but the living organisms today have a ratio of C12 to C14 in the atmosphere. Okay, we measure it all around the world, and it's 1 trillion C12 atoms to 1 C14 atom. So we're talking about big numbers, right? Trillion and 1. So we're talking about tiny numbers here. Okay. So when the starfish is alive, it's ingesting carbon from its environment, right? And what we find is that the carbon of living things exactly matches the atmospheric ratio, environmental ratio. And when they croak, it becomes a fossil, and as soon as it dies, it starts what? The C14 is no longer, the carbon is no longer being refreshed, so what's there starts to decompose, and the carbon starts to transform into from 14 to 12. And you get a different ratio, right? That makes sense. It's radioactive. So, just as an example, the number of half-lives, it's, say, if you have 100 trillion stable C12 atoms, you will have 100 unstable C14. That's a 1 trillion to 1 ratio. And the number of years dead is 0. The number of half-lives is 0. Okay, thing has been in the rock for a while. I mean, it's been dead for a while, and the amount of unstable CO2. Remember, now that the C14 is now decaying radioactively, and after 5,730 years, the amount of used unstable C14 is 1/2 of what it was before, and then 2 half-lives later, you've got 25 of these atoms, and in 3 half-lives, you've got 12 of these atoms, and it goes on. So when you get down to, say, you count 100 trillion carbon, stable carbon, and you find about one or so unstable C14, you think that's probably around 6 half-lives, which is about 34,000 years. Fairly accurate. Well, what's the critical assumption here? The big deal is that in all this time, the atmospheric ratio of C12 to C14 is always the same, right? Because if it was different in the past and the animal croaked, right? And we measure it according to today's ratio, we might be wrong. Does that make sense? Well, the scientists assume there's a thing called equilibrium, which is this ratio has been the same throughout the ages, all 4 billion years. Yes?
So what do they base that assumption on? It's just
that assumption.
That's it?
Make things work.
Well, uniformitarianism, the key to the past, I mean, the processes in the present are the key to the past. That's the assumption.
Huh.
It's a philosophical assumption.
Yeah.
As far back as we can go, we can see that might not be a good assumption if you look at all the statistics. If the assumption is true, the dating is a reliable method. I mean, we've got simulators now that can count individual radioactive atoms, so it's possible. Otherwise, C14 dating is not exactly as reliable as we thought it was. Oh, let's take a look. There was a very popular physics book called Tornado in a Junkyard. And it says, and this author was brave enough to say, assuming the flood did occur, little if any C14 may have existed before then. He says, we don't know. It may or may not have existed before then, and if so, this would give anything older than the flood, and that means the presumed time of the flood, a false appearance of great age. Isn't that interesting? Atmospheric levels of carbon. Well, what we know is that if we look at this from the biblical view, the Genesis flood buried vast amounts of carbon from living organisms. And these form coal, gas, oil, and all over the world. And what we've estimated, and it's mostly C12, is there's about 100 times more carbon in these buried segments, in these buried strata, than there is in the total carbon today in our biosphere. The world was rich in carbon in the old days, evidently. We say, well, there's not enough vegetation in the world to form any of these coal beds if there was a flood. Well, that's probably true because there was a lot more vegetation in the old days, pre-flood. It was lush. It was perfect. Everything grew splendidly. Trees that now are, say, like these lepidodendron club mosses that don't get more than 2 feet tall today or 9 inches tall, they were hundreds of feet tall in the past because we have the same species. We can tell it's the same thing that what we have today, and they were huge. The dragonflies had wingspans spreads of 3 to 5 feet. These were big critters. How big are they today? Not very big. The roaches were the size of Buicks. So what does this all mean? It means pre-flood, the biosphere levels of CO2 had a much higher ratio of C12 to C14. Because when we look at the coal and we look at these things, we can tell there's a gigantic amount of C12 there. Maybe higher. What could this mean? Well, there's two possibilities, and I thought about it. Was maybe the atmospheric pressure was higher. Okay, there was a lot more air pumped into everybody's lungs and systems. And that's why insects got so big, was because the only way an insect can grow and assimilate oxygen is through air pressure, because they only have little holes on the side of their bodies, right? And so air pressure is what drives it in. And the size of the insect today is as big as 14.7 pounds of air pressure allows oxygen to get to the inmost part of the body shape. However, if there was 2 or 4 times the amount, as an example, of air pressure, it would have an extraordinarily beneficial effect on the growth of that insect, and they could get much bigger because their bodies could grow bigger. They never stop growing. Their bodies would grow bigger because the oxygen could get to the inner parts. And surprisingly, when you look at the fossils, those insects are big critters, and the plants are big. There was just more something in the atmosphere. I believe it was higher pressure, and also you see how carbon-14 is formed, right? By cosmic rays. Well, maybe there was a protective cover around the Earth. It's like some crystalline shell, or I don't know what, or maybe just not as much harmful cosmic rays hitting the Earth. Remember, because it was a perfect world. So the C14 dates of fossils using today's atmospheric ratio will yield incorrect ages, and the ages will be much too old. Here's an example. Oh, I found a bone. Fossilized bone. And if I measure it with today's ratio, 16 trillion to 1, assuming today's ratio, this means half-lives expired. About 20, and it means it's about a 23,000 year age. Okay, 16 C12 to 1 C14. Remember, because it starts out trillion to 1, and then so we degrade the number of C14s in there. So it says, well, we've got a 23,000 year age. Well, suppose the C14 ratio started at 2 trillion to 1. Remember, higher atmospheric pressure or fewer cosmic rays? Well, then you would have 3 half-lives and not 4, and the bone would be 17,000 years old. And if it was 8 trillion to 1, which is 8 times, or about 8 times the atmospheric pressure, you would have had 1 half-life, and that thing would only be about 5,000 years old, maybe. Interesting, right? So if the atmospheric ratio was different in the past, the results are vastly different. There's a difference between 5,000 and 23,000 years. And remember, this is about the equilibrium. We said, how do we know? This is what the scientists say. What do they say? We know that the assumption that the biospheric inventory of C14 has remained constant over the past 50,000 years or so is what? What's that phrase?
Is not true.
Is not true. Did I answer your question?
Mm-hmm.
They know it's not true. So the key assumption is false, but evolutionists just ignore this. Isn't that interesting? We know this. So it's not as reliable as we think it is. Anything older than 60,000 years should have no detectable C14, right? That's what Garrett said. Right? By present, right? And if we detect C14, it's good evidence that the item is not really old. And coal should have no detectable C14 because remember, it's 350 million years old. But coal has C14 in it. Always. Fossil wood, estimated to be over 200 million years old, still contains C14.
How much?
Hmm?
You have how much in the spot?
Detectable amounts. I can get you statistics email.
That's the next slide coming up.
Diamonds, which is the hardest substance, and they're interlocked into a matrix that is almost impervious to anything. And they're estimated to be 300 to 600 million years old. Still contains C14, if you measure it. This is really interesting, because it kind of flies in the face of a couple of things. So, I don't think that those things are as old as they're made out to be. Okay, using their own standards, but you won't hear about this or read about this. Yes?
Do scientists now, I mean, because it seems like I've heard before that now they recognize that this is not as reliable and they rely more on DNA. Is that something that they use more now, or? I don't know.
Well, I think it's called scrambling. Okay. They're trying to figure out what to do about it. Actually, what they do is they say the way to date the way to date strata is by the index fossil in the strata. And we know the age of the index fossil because of its position in the strata.
So that's just as bad. It's a circular.
That's right.
And who created who identified what the index fossils were in each major layer? Who was it? Does anybody know? It was a guy by the name of Charles Lyell. And did he have any dating possibilities back in 1830? Absolutely not. And the dates that he gave were, where did he get them?
He made them up.
Paduma pulled the data out of midair. Okay? Paduma.
Or some other.
Or some other place.
Orifice.
Right? Some other place. That's where he got it. Okay? And remember, with the stratigraphy, you can have fossils on the bottom of a rapidly forming set of strata that are older, newer than the ones in the top.